My friends across the industry. Yeah, it has been long without sharing knowledge. As I told you, I always, with a little I get, I share because I believe together we can enjoy the industry. We can limit mistakes that cause sleepless night, and we can also inspire the younger generation to follow in our footsteps, because engineering sometimes is caring. So, and what caused the delay, of course, why took a bit of time was you have been aware that there was government plan to merge UNRWA, the mainstream Ministry of Works. I think the process started quite some time, December, and as we speak now, at least we are in a way somehow stable, because some of us managed to cross, but also others who remain behind their plans that they will also cross. So that is why there was a bit of gap in our knowledge sharing, especially from my side. You guys, you just wait and then you're not even commenting. Some anyway comment. We are sharing knowledge. That is from my angle. You also give me your angle. There are those philosophers who came up with all this formula, came up with all the design, research. We are now doing application, applicability. So that is what it is. Anyway, I know I talk a lot. And sometime around early this year, I went to Nairobi. I remember I posted something about Zenith Steel, and when we landed at the Jomo Kenyatta International Airport, that is when I felt welcomed. I felt that this knowledge sharing was not, I'm not wasting time. I'm creating a lot of friends. So you can imagine the person who welcomed us, who came to pick us from the airport, he was already my follower. And he called me by name. We were about 6-7 people, and they said, "Hey, Bwana Ochola Mike, Karibu, Kenya. How are you? I always enjoy your YouTube and not seeing you physically." So from there, the rest became story. But one thing he made clear to me was, he said if I could share a bit of knowledge also in bolted splice connection, it would be better. He was trying to do, and he's not so much needed some knowledge. What from my angle, I've followed it up. So I said, okay, fine. I will. The good thing, we were taken through at our master's level when we were doing steel composite concrete and steel concrete composite bridge, and they took us through, so we understood few things. So there were two things. We talk of tension balls and preloading balls. Then I said, okay, fine. Normally when we talk about high strength friction grip balls, that is where normally slip become concern as a visibility limit state, and so these balls tend to compress or pre-stress or create a friction surfaces whereby the response or resistance to shear is always by the surface between the web and the web plate. So, and because balls are considered as stress risers in event of cyclic loading and what we call fatigue, So normally it is important. I think researchers found that it is better if they use that. So that is why even it is important that the surfaces at the area where we are where we are going to where we are going to do the connection is rough enough intentionally so that it can. Normally we use a coefficient of friction of about 0.5, but it varies depending on the surface. So this is basically a robot structure analysis professional software. This is a research software. I think we had a training recently, and they gave us the student the research work, not a commercial one, but a research-based access, which we are using. It's not pirated, but we had a training under the Ministry of Works and Transport. It was organized under the bridges and drainage structures, which I think took about 10 days. So if you look at this arrangement, we have the web. This is the web plate and the web balls. These are the flange. In principle, always they say if you're designing by hand, they say moments are taken by the flange or flanges, while the and the bottom flange become critical if it is simply supported or at the bending point, and they become critical near support and the rest of it where there's also holding and the rest of it. Then the web plate handles shear. These handles bending. Basically, that is that. So this is just a 3D thing, which I look at it in detail a bit, and that is so. There's an outer plate which goes the full width of the flange. Then you have the interior one, which you also need to note, because somewhere when you're modeling this, it will ask you. So sometimes you may not. In some cases, if the bending is not too much or moment is not too much, you may not need even the upper one here. They only use the top and the bottom flange, not the interior one. So that is that. Now, but where do you start from? As a designer, you have to start from somewhere. You have a deck. You have a deck with about you have a deck with about four girders. You have 1, 2, 3, 4 connected with diaphragms, and this is 3D. You do your modeling, everything is done, the span is given, and so. But at the end of it all, the engineer, he has done his design of the slab, he has done his design of the steel composite at construction stage and at service stage. Now it's left with the key one. How do you connect a girder? If you look at the span, it's 25.6 simply supported. Now that means if your girders are coming at maybe 12 meters or 11.5, depending on the factory, the length, it means now if it is 11.6, so what is remaining here, it will again remain 11.6, mean now you are left with 14. 14 is again more, so you have to now know you split, so that's about 7. So that will mean you have 7, you have 11. So a full piece is 11.6, and then you have to now split the other remaining one into, so you have 7. So from 7 from the support, you have a joint at 7 meter. Then from the left hand side also you have, so from this side to this point you have support, and then there is support. So if I come down here, so you find you have something like this. So somewhere around here you have a 7 meter, around here you have a 7 from this support. So normally what happens is the principle is you have to be away from these high stress zones. You have to be away. So we normally tend to have the full piece run in the high stress zone, high bending moment, and then where there's less bending is where we put the joint. And also we also need to balance with high shear. So you find from the support you have high shear, but towards the middle you have the shear reducing. So you try to do that, you balance. But normally for voltage Splice connection, I think we have about 3 forces we to look at. We look at the bending force, we look at the bending, we look at the shear, then we look at axial load, so axial forces, which we look at. So because these balls tend to undergo to respond to axial forces, to shear forces, and to the bending forces. That is very, very important that you must be aware. And they respond at ultimate limit state and as well as serviceability limit state. For the high strength friction grip ball, be mindful that you should not allow slip to happen at the surfaces at serviceability stage or at service when they not at limit, not at the ultimate limit, but at the service limit state. Make sure the slip does not occur, because if the slip occurs, then you initiated the weakness and the weakening of the joint. So it is very, very important. So when you do your design, it is very important. At the end of it all, now the engineer will extract this information from here, and then from there. Normally, when you are modeling using Midas, there's where you have to specify where the splices will be. So you are keen to know that at this, you see, I think this was you need to know. Then you pick moment exactly at the splice connection, and that communication must relate to the drawing. You can't pick a 7 meter and then later on you do what? You can't pick a 7 meter, then tomorrow you say it is 7.5 or 6.5. You change. Definitely it's not going to be the right way. You're going to get into a problem, and which is not very good. So we need to be mindful of negotiation. That's why they always say whatever you do must communicate. Must communicate. So you, as a designer, you must be mindful. So having done this, you have all that, then now we should be able. So this is the kind of a typical something that, which, like you're a young engineer, you have not been in this, since this is knowledge sharing and more for the young engineers. I know you look at this kind of some of the balls are here. This, I think, is a tension control ball. It's a black in color. You have this picture here. Then you have shear connection. And so here also there's a way you do, how do you place the shear connection, but this topic is not for shear connection. So you have the top flange splice, plate. Then there's a fill plate. I think here they did something because this joint, this web, this flange is different from this flange thickness. So there's a fill what to avoid creating, straining this top. Now because they flash down here, this level, then up. So the same. So they are connected to, of course, optimized sections where the bending, where the bending requires thicker flange. That's why you can see all this. So now this is a typical connection you can see, and it is not very far from what you are seeing here. Or no, I think I want a different place. I wanted this one. So this one is not different from this one, so it's typical the same. So that is what need to be done. And so I think here this was the layout was given a typical, but now my point here is, where do we start from as an engineer? You start from here. When you design your thing, then you come and pick all these moments at ultimate limit state and also at serviceability limit state. Pick the moment, pick the shear, and pick the axial load. So having done that, now you have, for this one down, there was a typical plate girder, which is a 1.5 meter depth by 600. That comes out from your design up. So the girder web is given a 15 meter thick web, and then the flange is in that. They've given you the girder resist bending moment of that, axial tension of that, and shear force of that. Normally from the lecture room, that's what they will give you. But now when you're a real designer, you are the one to pick. You get it. So from there, this was a typical extract for lecture. For us, for lecture, this was our exercise. So you can see they picked everything here for us. It's if it is very deep and it's not too much, then you can see that actually a single line is okay. But sometimes when you do calculation, then you see this one. Then you ask yourself, you see here, because it's shallow, it's only like 1 meter or 900. You need more. But if it is deeper, then you can see that one single line is good enough. So, but that comes up from when you are interactive design. So you have the ultimate limit state of given bending moment, axial loads, and then shear, and then yeah, basically I think this is now where normally you need. But then there are also limits, serviceability limit state moment needed to be given forces here. So when you have all that now, what matters is now for you to get to, when you come here, you are supposed to come into this. When you have opened your robot structure, I think there's idea statica, but I think yeah, but this is the one I'm using because at least there is it's authenticated version whereby it's for the training and then also for research. So you have a connection details. You have to put the splice connection, beam splice is given here. Then the symmetry connection, you can actually click. So there are different types here you pick, but for bolted connection, this is the one because you are going to have the inner plate and the outer plate and then the web plate. Now that gap always about, that S1 is about 10 millimeters, because yeah. And even these ball holes, there is a gap of about 2 millimeters. You allow the steel, because steel expand and contract, allow the steel to breathe in and out. Breathe in and out to control stress. The way you do it, as if you close your mouth and the nose, what happened, you get it problem. The same thing if you do for steel, you see many problems coming up. So, and then now the girder is given here. You see here, I was using this girder here, which is on the 900. The other one I showed you was 1.5. So definitely we have less shear steel in the way. So then the grade is given, the bolted is given. Please take note of all this. Then you come to general setting. In the general setting, the same thing, the material to be used. If the materials are different, then you also specify the same setting for all. Then here they are using M24 bolted. Normally for high strength grip, high strength friction grip balls, normally they use a 10.9 great balls. The lower one are normal for buildings and the rest, but for bridges, I think that is what. But of course, you can do research and get the reason behind it. It depends, but that's what. So here you can either do threaded area or unthreaded, depending on where you tie the nuts is threaded. The area is less. Then when your thing is on the lower side, the area, if the ball is M24, so the threaded area, definitely the area become slightly grooved, will not be the same with the shaft. So you have to be mindful of that. And then you can also check this to whether it is threaded or unthreaded, the shear plane. Of course, one has a reduction of the area, one is not reduced. Now this area BACD, this is now the area for bridges, for bridges and surfaces. This other one are for building and the rest, so you have to spend. Now here you can change. This is now where, are you sure at service or during operation the factory will produce this exactly? How do we test for this? So these are some of the areas that's why we say knowledge sharing. Other people can tell us what happened, the slip factor in reality, but that's what it is. Sometimes they bring the girders when they're galvanized, some even painted. When you paint this surface, do you still have the 0.5? So it is very important that you take note and follow up as a supervisor, as a designer. What are the special areas you need to pay attention to when they're doing the fabrications and then also installation. Remember, for steel composite, most of this structural steel, you do factory like shear studs. This connection detail must be done from the factory control and high quality control deliberations, X-ray control of the welding areas, and the rest. The ball must be to precision. Then they do side bolting now. That's very important. So some of these surfaces also need to, this factor here, very important. That means the sub drawings that go to to the factory of fabrication must have the slip factor given and all this detail. Very important. And then that's it for general. Then now when you start on the web, you must specify the website. You see here, this thing here, you can see. You need to know that website, yeah, the web, yeah. And then you need to know the spacing. So if I go back, it's okay, fine. It's the same. So you get to know the horizontal in this direction and up. Very important. That is the and it's defined all here. That is the length, the horizontal, then the depth is one. And be mindful that there should be no conflict with the flange here. It will cause a lot of problem. And then the thickness is always given. Now after that, then you can now do you are done with the web detail for only for the flange. The balls will come later. Then you go to the upper flange. Here also is given the length. You see even here is given the width as per the flange. Sometimes it is reduced inward, and then also the length. You specify that, and then the thickness also you have to specify. It may not be necessarily the same thickness, or the force will give you that. Then internal plate parameter, that's the one. These are the internal plate parameters. So you reduce this thickness from that top, deduct it, and then allow some allowance, because there will be a weld here, maybe 6, 7, 8, or 9, or 10. You deduct it, allow that to fit well, and then we shall also look at the spacing requirement later. So you specify that. Then the lower flange is the same thing. You now know this one here. This is the same as up here. The same, just like a replica. But you also, one thing you need to know here is, if it is simply supported, sometimes this flange here, so this can be longer than that, and the balls here can be more up, can be less than this one. So that is something you need to know. Very, very important. And then the web bolt now is very important. Now you need to know basically the spacing, the rows. It is iterative at also, most of this design we do. You first do it, start with single line, then move to the double line. You'll see the results coming until you get what works. So the spacing are all given, what you need to know, the rows, the arrows, so we are going to see the requirement of E1, E2, and P1 and P2 down. So they are all specified here. Even the upper plate flange, the E1, E2, blah blah, those requirements are code guided. What would be the minimum spacing of bolts? The same with if you're doing piling, the way you do piling is the same way you do the bolting. The minimum H distance, though for piling said 1D. If the diameter is 1 meter, then the minimum H distance from the edge of the pile cap is 1 meter to the center. That is what it is. But I think we shall see how the bolt is done. So the whole here, you have the number of columns, you have but this is not exactly this one. This is now one you're entering another one. The number here, the number of columns are 1, 2, 3, 4. Because it's symmetry, it will replicate the other side, so 4. And the rows are 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's how you get it. So from here, the lower plate also you do the same. Having done all this, the next stage now you go is to go to the forces. These forces is where now you pick. I told you. You see axial force, you see shear force, the bending. That's the ultimate limit. The right hand side, the left hand side. Remember, this thing has got both the right hand side and left hand side separated by that gap of 10 millimeter. So the loading, you can see even the nomenclature of the loading. You can see all here. Very important. Go back to your theory of structure. So these are typical values they have given, but you will have to pick from where you have where we did this one. You would go back here, and then you pick them here. The typical values you would pick from here. What is the value around here for the bending moment? What is the value at the shear? Get it the right one, and make sure you know the worst combination is what you're going to be using. So having done that, then so for ultimate you specify all of them here, left hand. This is typical here. Then serviceability limit state also here and there. Please, most of these forces you have the ultimate limit state output and then serviceability. Make sure they're all here. Then when you click calculation, then it will now take you to, you click, having done all this now, because it is first of all the geometry. When you're done with all the geometry, now you go to the force. So you click here. So it's going to run the design. So the design is out. and it's telling you it has failed, the ratio has gone. So your ratio must be less than 1. So now it is from here that you start. What happened? Why has it failed? So there is already an output somewhere here that I needed to share with you. So that will be the output. You can use the what is typical here. So now he's telling you calculation of the beam to beam splice connection. The Eurocode is given, robot structure is given. These are the different geometry, the way you see it. That then now you want to know why has it failed. So where it has passed, it will give you verified upper plate. So these are the dimension, all of them, dimension, detail, labeling, and then parameters. So we now output start from material factors given. Now these are all what you were specifying one by one. At the end, so where it is said verified means they have all passed. Ball connecting a splice plate with the beam, where ball capacity, I think they have all passed. Ultimate limited, ball shear, all passed. Ball connecting a flange, they're all okay, verified. First rate, serviceability limited, ball shear, problem. You look again, come down. So shear into the ball is a trouble. Serviceability limited, ball shear, not verified, means as failed. You can see a factor here. The load, this is it. This is applied, it is more than the capacity. Then you come again down. Verification of section due to block tearing. Still down here, you have a problem of beam. So a beam also has a problem. You get it, eh? So it can either be a plate. So upper external plate has a problem. Upper internal plate has a problem. And then, so you begin to, that's now your first iteration. You're going to go and check what is it. Is it the thickness? Is it the what? You see here, the forces are not, they are not meeting. Here, the applied are less than resistance, but here now, so these are the actual stuff. So this is what you look at now at the you see most of this upper plate, they're all failing, and you need to know area or tension zone, blah blah. So all down. So finally down, you see it is saying connection does not conform to the code. It is failed. So you go back. When you go back for the iteration, you start. So that is the most important thing. So you would go and you try to see that maybe it is the depth that you need to improve, or the thickness of this, or get it, or the web. You have to keep zigzagging here, doing iterative, and you run until you get that. Very, very important. So something I wanted to share with you here. So that is what it is. So I'm going to look at the requirement of the bolts and the shear. Definitely, the splice connection is designed in accordance with the EN 19 blah blah. These are the references you do to take for bolt connection, and bending, shear, and axial forces. These are governing standards and design philosophy. Design follows ultimate limit states. Of course, you check for sustainability. Now here you see it's telling you the plate types will be inner plus outer, inner plus outer, and then the web has to be both sides. Or for symmetry and also having better stuff. So what is happening here is, okay, for ball grade 8.9 or 10.9 preloaded if slip is critical. Preloaded if slip, so preloaded balls are for high strength friction grip balls. Diameter, they give you spacing. This is what I want us to be mindful of, is the spacing here. You see ball specification and layout. Spacing and edge distance. So for longitudinal pitch, that is the spacing, interior spacing, which is here. In anything in here, in this direction, and also in between in here, in this direction, and also in here, interior. They're saying it has to be at least 2.5D. If the ball is 20 millimeter diameter, that means our tendon minimum should be 50. Transverse also the same, should be at least 50 for a 20 millimeter diameter, or 30. If it is 30, it should be at least 75. If it is 24, it's around there, about 6, 5 or something. Then end distance, they're saying at least greater than 2D, while the H distance will be about 1.2D. This is EN, but if it is Eurocode, it would be about 1.2. No, if it is VS, I think 1.25. So you can look at the different codes, but what I'm saying is, whichever code you're applying, make sure all this, the spacing, don't just make it random. Normally, even when they submit for you this report, you check, they should not be random. They should comply. Reference is given for EN, Reference is given. Yeah, you can check. And then I think that is what I wanted in this spacing. The rest now. And then in terms of the bending, I told you the lever arm, for those who do calculation by hand, it's very important when the moment is given, you need to know center of the top flange and the center of the bottom flange is the lever arm you get. Then now dividing it, you are going to get the force acting on the balls. And then from there, you add on few things. I think they're all given. The absolute load as the horizontal force that will cause on this ball to fail. And then you start calculating how many balls you need, whether it is balls which are. So basically, I don't want to go into more into that because they're all given, but at least the procedure and how to follow. So once you get your force right, you do your calculation right, you pick the right moment. Please, normally people make mistake. They end up picking moment here. You'll be in trouble. You must know that these girders are not full length all the way. Even if full length, you can't design a bolt around here. It will be, you are going to have a 2 meter deep, even 3 meter deep section, and you're going to have million balls. So you have to pick them from this side, and then you're able to pick the right shear out, and then the actual load, and then the right configurations, the dimensions. You specify the drawings will be coming out. Your drawing must also comply with the spacing of the ball and minimum end distance, minimum H distance, and then the minimum. You do that. If the minimum is not passing, then your iteration comes in. You adjust, or you add more balls. You add more plate. No, you lengthen the plate, or you deepen the girder. So I think basically that is what I thought I should share with you to follow this. So once you get that one, please, this is a very good one thing. Also, I realize I've been talking too much about Midas. Now I think Midas also has its own limitation, especially in the connection detail, joins, base plates, and other things. So here is where you come in and try to work. Make sure this one is not, if it is failing, please you check all this verification which I've given you. The rates must all be green. Then from there you should be able to smile at the end of your design. With this few engagement, ladies and gentlemen, I remain Michael Chola, PMP, a registered engineer with Engineers Vision Board of Uganda, a member of Uganda Institution of Professional Engineers. I also told you I'm a member of International Road Association Bridges Technical Committee, the year 2024 to 2027. I'm learning. There are very, very senior professionals across the globe that we learn from. These guys are good. They have seen bridges and they have done bridges. I do appreciate. I have one mentor there called Mr. Gill, Professor Gill from Korea. He's my immediate, so I consult him. So very, 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 very. That's the immediate one I know, at least on the team. And I've seen him physically. He's also coming to Uganda soon, so I'll continue. If I want to specialize in one of the areas in bridges, I think he's an immediate person I will also look at. Also have another Japanese engineer called Shakai. He's also one of the most smartest guys around. But we shall learn more and more and get them. So I urge you, the young guys, work hard. I don't have a PhD, but I want you guys to get yours. Me, I don't need that one. I just learn a few structures. So I think this is okay. This, I think, Mr. Odinga, please, you can have this. If there's anything still confusing, please send me a WhatsApp, and then I can clarify a few things. Thank you so much, and you guys, blessings this Sunday.